In previous videos, we tested a small motor, established its transfer function, and tuned the PID controller parameters. In the next few videos, we will test a true industrial-grade geared motor, attempt to establish its mathematical model, and apply it in practical engineering. In this video, we will first build a friction model for the strain wave gear rotary actuator, then use this model for friction compensation. Finally, we'll demonstrate the gravity compensation effect after adding friction compensation. Let's first look at the final test results. This is a strain wave gear rotary actuator with a 100:1 reduction ratio. It drives a 2 kg iron plate via a 16 cm linkage. After adding friction and gravity compensation, the entire system behaves as if there's no resistance or gravity. It can rotate freely. A light touch by hand can easily make it rotate or stop. Part 1. Introduction to the test platform. 48 VDC regulated power supply, test bench, linkage, iron plate, motor output shaft, Link debugger, microcontroller STM3203CAT6, CAN communication module TAJ1050, USB to serial converter, USB CAN debug box, industrial strain wave gear rotary actuator, model EROB 70H100i, 100:1 reduction ratio, rated power 100 W, rated voltage 48 V, rated torque 10 Nm, peak torque 70 Nm, max speed 30 RPM. The structure of the strain wave gear rotary actuator is as shown. Part 2. Identifying the friction model for the strain wave gear rotary actuator. Under no-load conditions, we conducted speed loop tests, measuring the average current at different motor speeds. This allowed us to plot the friction curve shown here. Friction is a nonlinear function of the motor's actual speed. The x-axis shows motor speed in RPM. The y-axis shows friction represented as current in milliamps. Numerically, when the motor speed is 0, friction appears as static friction. When the motor speed is non-zero, friction increases non-linearly with motor speed. The friction curves for CW/CCW rotation are symmetric about the origin. The video adopts a lookup table-based mathematical model to precisely describe this friction. Due to symmetry, only the positive half-axis data is stored. The table contains 37 points, using piecewise linear interpolation to meet real-time computation requirements. Here's the test result with only friction compensation enabled. A light touch by hand allows the motor to rotate and stop freely. After adding a 2 kg iron plate, a gentle push on the linkage causes the motor to swing with constant amplitude, as if there were no friction. Part 3. Identifying the gravity compensation model. As shown below, the current required to counteract gravity depends on the motor's torque constant, linkage length, iron plate weight, and motor angle. The first 3 parameters can be combined into a constant K. With the motor in position mode, held at 90 degrees, we measure the current to calculate the value of K. The complete friction and gravity compensation model is as follows. In real time, based on motor speed, compute friction compensation current. Based on motor angle, compute gravity compensation current. Sum both and send as torque mode command. This achieves full compensation. Finally, let's see the full demonstration. In the next video, we'll establish the speed loop model for the strain wave gear rotary actuator. Stay tuned. The strain wave gear rotary actuator and test bench used in this video were provided by Zero Control Co. Ltd. Special thanks.